Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to the course on Mathematics of Data Science. In this introductory lecture, I'm going to be talking about the evolution of data science. I'm going to argue that data science is as old as science itself, even though we tend to believe data science is something new. Data science has its beginnings in early astronomy. Much of what we know in physical sciences had their origins in astronomy. In those days, the only thing that we could do is to be able to observe the positions of various planets with a handheld telescope. Thanks to the Herculean efforts of pioneers, Copernicus, Galileo, Kepler, Newton, and a whole host of others who have contributed to the foundations of data science starting in those early days. In the early days, they collected observations. They knew nothing about how Mother Nature behaved. The amount of data they collected by hand was enormous for the technology of that time. They probably did not have the pencil paper as we do. So they had a means of storing the data that was collected, and then they started analyzing the data to be able to understand the hidden physical laws that the data may reveal. It is based on this analysis they discovered the heliocentric system as opposed to the geocentric system. It was believed that Earth was the center of the universe. No, that was wrong. Based on the observation, we can show that it's the sun which is the center of the universe. This fact came out as a result of analyzing the data about the positions of various planets, including the sun. The next one is the laws of Kepler. Kepler, in my view, is the real founder of the data science. He had over 30 years of data meticulously collected, stored, and he started analyzing this to be able to understand the patterns hidden in the observations relating to the positions of various planets around the sun as a function of time. We all now know that Kepler found several laws. The first of it says that Earth revolves around the sun, with the sun in elliptical orbit with the sun as the foci. And the chord, which is the line joining a point on the ellipse to the foci, that swept equal areas in equal intervals of time. These are tremendously important laws at that time, and he got these rules, regulations about the motions of the planet based simply on analyzing the data. So data to law, data to model. Then came, standing on the shoulders of Kepler, he found out that there is an underlying gravitational attraction which makes the world revolve around the sun. So within the context of physical sciences, these are some of the earliest examples of the movement from data to model, which we now call data mining. Data mining is a big part of data science. So now I have been arguing that data mining is as old as science itself. So what is data mining? Data mining is the process of extracting the structure or patterns that are inherent in the data or observations. These patterns give rise to understanding the generating process. If I can understand how the motion of the Earth around the sun goes about in its journey, I should be able to generate the positions of the Earth around the sun and I should be able to make predictions about its positions. So it is these patterns reveal the secrets about the motion of planets around the sun. So the goal of data mining is to understand the data generating process. So we want to go from data to data generating process, and that relates to from data to model. I'm going to use the word laws, model interchangeably. So since the motion of the celestial object inherently followed certain laws which we didn't know at the time, early pioneers with their hard work and ingenuity could discover the laws that laid the foundations of physical sciences and engineering as we now know today. Now fast forward. Today we have very cheap sensor technology, we have very powerful wireless communication, we have been able to store thousands of terabytes of data, large-scale storage devices. Of course, we have powerful supercomputing machines. So it is the confluence of sensor technology, communication technology, storage technology, and computing technology together has ushered in a new era for data mining, data science. It is estimated that the amount of data collected doubles in every 2 years roughly. So today interest in data mining include physical sciences, biological sciences, space exploration, all of engineering, environmental sciences, medical sciences, economics, finance, sports, recreation. So it is there everywhere. I will come back to data mining a bit later, but I want to now build another line of argument going back to early days in astronomy. Newton was standing on the shoulders of Kepler. In high school textbooks, it is often written that Newton was lying under an apple tree on a spring sunny afternoon. The apple came down. He asked the question, why did it come down instead of going up? He discovered gravity. That's a beautiful story for 6-year-old kids. But by the time Newton came into the scene, Kepler, Copernicus, Galileo, they all have recorded all their findings. So standing on the shoulders of those pioneers, Newton was able to realize that the position of the planets around the sun relates to understanding the motion, and that needs dynamical descriptions of objects. And they did not have a tool at that time to be able to describe the dynamics of the planets. So he, in tune with Leibniz in Germany, they developed the fundamentals of calculus, differential calculus, integral calculus, differential equations. Once they had that mathematical tool necessary to be able to capture the dynamical aspects of the motions of the planet around the sun, he was able to describe the motion in terms of a mathematical model, which we now call differential equation, ordinary differential equation, to capture the motion. Once you have a model like that, I can make prediction by running the model forward in time. So as early as Newton's time, we were able to go from data to model to be able to make predictions. So to me, those are the beginnings of data science, how the fundamental laws of nature were discovered. With the availability of models, the potential for forecast or prediction became very clear. So until now, we saw data mining, development of models, and the ability to use the model to be able to generate the data that observed and also be able to predict the data at a future time. Now there is a second strand. DM is data mining. DA is called data assimilation. Data assimilation is a fancy word for estimation in principle. So here's another story again that's coming from astronomy. Gauss was a very young person, 24 years old. At that time, astronomers were observing an object called Ceres. It went out of sight. It went into the shadow of the mother planet. So they did not know where it went, when it will come back. So that was a major open problem in astronomy of his time. So this young man took up this challenge and he solved it completely. So I'm now going to tell you the methodology by which he approached the problem. So he knew that people have observed the positions of the lost object over a period of time. He knew from Kepler's results that this planet must be going around its mother planet in elliptical orbits. He argued ellipse is a two-dimensional object, mathematically is a variable in two variables, x coordinate, y coordinate. The general equation for an ellipse is a second degree polynomial in two variables, ax square plus bxy plus cy square, dx, ey, and f. So there are 6 parameters. He said, while this second degree polynomial describes the whole host of all the ellipses that one can have, of course there are conditions. Not every second degree polynomial is an ellipse. So he decided, if I want to be able to specify the particular path that this lost object must have been following, I must be able to estimate the parameters a, b, c, d, e, f. So he formulated the problem. I have a model with unknown parameters. I have data relating to their positions. Why not I bring the model and the data together and use the data to be able to estimate the parameters of the model? So he was the first one to be able to introduce the notion of parameter estimation of the models using the data that is available at the time. And this aspect of combining the model with the data is called data assimilation. To assimilate, our body assimilates food. Immigrants get assimilated into the existing society. Assimilate means to become one with, part of. So I am going to assimilate the data with the model. Once I have estimated the parameters, that model is called assimilated model. Using the assimilated model, he was able to make the prediction. But the important thing to recognize is that he invented the method of assimilation called method of least squares. I'm sure every one of you must have had an introduction to method of least squares. So method of least squares was invented by Gauss at that time to be able to solve the open problems of his time. Now let's see, we have already talked about two major inventions, the invention of calculus, the invention of basic rule, the laws of Mother Nature, now the invention of method of least squares. So with these available, now I am able to pull the model closer to the data to get the assimilated model. Once I have an assimilated model, he could run the model forward in time. Again, he used Kepler's result. What did the Kepler's result say? The chord sweeps equal areas in equal intervals of time. So he was able to run that model forward in time, make a prediction. He made a prediction about the bearing and the time. Sure enough, it was a grand success at that time. So this young man at 24 years old solved one of the major open problems of his time. In that process, he also invented the method of least squares. So this work led to the foundations of what we now call data assimilation. Data assimilation and the method of least squares is a workhorse of the data science industry. It's a basic aspect of statistics. But he was also having another challenge. The data of his time were handled by people, handwriting what the observations were. There were lots of errors. So he wanted to analyze. He knew the quality of the assimilated model depends on the quality of the data itself. So he took up the second problem of being able to analyze the errors in observation. He then invented the bell-shaped curve, the Gaussian distribution. So in addition to inventing the least squares method, he also found out that the errors in observation follow the standard bell-shaped curve, which we now call normal distribution or Gaussian distribution. So Gauss, after having invented these two side products, he was able to solve the open problem of his time, the bearing and the time at which the lost object will appear, and that was the first successful prediction. So you may see in my slides, I have introduced inverse problem, forward problem. So I'm now going to elaborate something on that. What is an inverse problem? If I have a model, I can run the model, generate data. That's a forward problem. Prediction is a forward problem. But if I have data, I want to uncover the model itself. That's an inverse problem. I have a model, I have an unknown parameters, I have data, I want to be able to bring the model and the data together to be able to estimate the parameters of the problem. That's also an inverse problem. So mathematically speaking, much of what we do in data science belong to one of two categories, is either an inverse problem or a forward problem. So we have touched upon lots of different aspects: data mining, data assimilation, discovery of basic results, namely calculus, least squares method, bell-shaped curve, the notion of inverse problem, and forward problem. And please understand, these are as old as science. To me, this is the time at which data science began, even though they didn't call it data science. The word data science has been prevalent only within the past 10 years. So I would like to argue that it is the basis with which the entire scientific process progresses. So the data science is much more than what we now tend to believe, perhaps. So what is data assimilation? Data assimilation is called fusion of models with data. Models are general descriptions of the underlying process and questions. Data or observations reveal the secrets of Mother Nature. So data is here. Data contains the truth about Mother Nature. Models are here. Models are our understanding of Mother Nature is. So data and models generally often don't see eye to eye with each other. I need to bring the model closer to the data. Models in general have unknown parameters. In the case of elliptic parameters. In the case of a dynamic model, my initial conditions may not be known. The coefficients of the differential equation may not be known. The boundary conditions may not be known. But I only know, in general, this class of model describes the phenomenon. So if I want to be able to find the special type of model that could explain and help me to predict the specific phenomenon, I have to bring this model and the observations of the process together. This aspect of being able to bring the model and the observation together is called data assimilation. The assimilated model is a good tool for creating forecast or prediction. One of the standard tools for the fusion of models with data is based on the method of least squares. So the goal of DMDA is to generate a good forecast. Please understand, much of what we do in life is driven by the need for prediction. Please understand, the development of various things were propelled by the need to be able to predict where the astronomical object will be. So much of what we do in many aspects of science depends on the need for prediction. I'm going to give you some examples of that. Madras was hit by a hurricane. Hurricane is cyclone, cyclone is hurricane, very recently. In Bay of Bengal, the hurricanes form south of Andaman and Nicobar, a low pressure system. It is closer to the equator. The water is very hot. So if there is a low pressure system, there is a lot of evaporation. The heat through the evaporation feeds into the low pressure system. Then I need to be able to predict whether it's going to go to Bangladesh, Calcutta, Orissa area, or Visakhapatnam, or Madras, or Rameshwaram. So there is a whole angular domain over 200 plus degrees. It could move in. It could move in. So hurricanes are simply rotating phenomena. They are being pushed around by the prevailing winds. So I need to understand the prevailing wind patterns to be able to see where it will hit. We can't stop the hurricane. By making good prediction ahead of time, we can save the lives of humans and animals. So predicting the path of a hurricane, in the United States we have another whole close cousin of hurricane is called tornado that happens on the land. There are several models for both hurricane and tornadoes. The data about the hurricane generally come from satellite. Please understand, south of Andaman, about 800 miles south of Andaman, very close to equator, we can't go and measure. So we have to depend on only sensing devices such as radar and satellite. Radar reach is not good enough to be able to go that far. So we look at the starting point of these low pressure systems from the satellite data. Then we have general mathematical models. We collect data from the satellite, we collect data from the radar, we ingest that data into the model. Hurricane happens in Atlantic, hurricane happens in Bay of Bengal, hurricane happens in Sea of China, hurricane happens in Japan. The geography of these places are so different, but the general model of hurricane as a mathematical model is a generic model. So I need to be able to specialize the hurricane model for Bay of Bengal, hurricane model for Sea of China, hurricane model for Atlantic. That specialization comes from combining observations with the generic model for hurricane to be able to make a prediction. The next example, a crime happens, detectives come and collect data. Their aim is to be able to understand the nature and the type of operation that criminals may have used to be able to identify who may have the capability to commit this crime. So every crime scene operation involves basic prediction. To be able to generate the basic prediction, they have to collect data. Please understand, every crime scene detective go from data to prediction, and they have their own class of models. So what is the idea here? We are not the only one in computer science and data science using data science. There are people in weather modeling. One of the major jobs is to use data science. Crime scene investigation, they use their own models, method of collecting data to assimilate the model to be able to make a prediction. The next one is an interesting one. It's called NTSB. NTSB is called National Transportation Safety Board. Air travel is by and large one of the safest forms of travel. There are probably more than 1,000 people die on the road in India every day. In United States, during long weekend, let's say during New Year's Eve or our Independence Day, they will make a prediction. During the next 3 days, there's a likelihood of 700 people who may lose their lives on the road. And then after holidays is over, they will say, well, we were correct up to 5% error. In India, I don't think we collect data. I don't know whether anybody collects data about the deaths on the road. So more people die on the road than air travel, but when a plane crashes, it becomes a huge news. So what is the job of these NTSB engineers? They go cordon off the area, they collect all the debris, they try to reconstruct the plane and see which part is missing, how the elements were sheared, and based on that data, they then try to find out what could have gone wrong. Is there a feedback I could give to the designers to make things better? So from data to model to predict the causes of failures of aircraft. And that's what folks in NTSB are doing. It's a very huge organization. Wherever across the world, if there is a plane crash, they come and take over. And they are extremely bright group of engineers of many different types. The next one, every government at municipality level, state level, federal level, we all need to be able to generate budget priorities. How much education gets, how much railways get, how much anybody else gets. To be able to allocate money, I need to know how much money I'm going to have. So there are economists whose only job is to be able to predict the total amount of revenue that the government will have available for distribution to various departments during the next budget year. And that involves analysis of time series data. So there are lots of people within government at every level who are interested in trying to understand the tax generating process, how much money I'm going to have to be able to make the budget priorities next year. Last but not the least is the medical diagnosis. You don't feel well, you go to the doctor's office, you start describing your problem. If your problem is simple enough, the doctors will write a quick prescription and go get it, and you are done in a couple of days. Sometimes your oral description may not be sufficient for the doctor. He may want to collect other data, blood test, with me, X-ray, MRI, and so on. So each one gives the data of your current position. An ideal body, what it should be, is an anatomy book. That's a model. The doctor knows the anatomy book. The doctor finds out how your present condition differs from what it ought to be as per the anatomy book. Everybody with my place? Then he tries to identify the cause for your problem. Then he prescribes the cure. With me? So every medical diagnosis is collecting data about the patient, trying to determine what the problem the patient is suffering from, and then being able to develop a cure for the disease that you may be suffering from. So these are examples: predicting the path of hurricane, crime scene investigation, estimate the cost of failure, prediction of potential revenues, medical diagnosis. I'm sure you can add many more to this. So what is the idea here? The idea here I want you to think about, we in computer science are not the one, we in information science are not the one who is data science. Chemical engineers do, mechanical engineers do, doctors do, detectives do. So analyzing data, combining models and data is a very fundamental aspect of analytic techniques that everyone have been using, even though we now have come to call it as data science. I'm not trying to diminish the importance of data science, but I want to tell you how it grew up. It did not come out of the blue sky 10 years ago, even though the departments have been popping up. There are departments of AI, there are departments of computer science, there are departments of data science, and so on and so forth. So the departments have been popping up. Okay, the model is supposed to be in between the input and output. So I'm now going to get a little bit more mathematical to be able to describe the difference between inverse and forward problems. Forward problems are also called direct problem. So direct inverse or forward inverse. So I have a model, I have an input to the model, I have an output to the model. If I am given the model and the input, if I want to compute the output, that's called the forward problem. When you are in college, you learn to solve forward problem, how to multiply two matrices, how to solve a linear equation, how to solve a differential equation for a given initial condition. Okay? So the math, how to solve a nonlinear differential equation numerically. So while in college we learn to understand problems posed in the forward way. I am given the model, I am given the input data, just ingest the input data into the model and let the model run. Let this, we call it solution. There is no difference between solution and prediction. It depends on the point of view. So sometimes I may know the input, I may know the output. I may want to identify or estimate the model parameters. That's an inverse problem. Look at medical diagnosis. I go to the doctor, I'm not feeling well, I show certain signs. The signs are exhibited by blood test, urine test, or whatever other test you have to have. Then it is those tests are the output. Then the doctor will ask you, what did you eat yesterday? What have you been doing for the past few days? Then he knows the model. Then he wants to be able to solve the inverse problem. This is, you are facing this because of these. So I'm going to remedy this with these kinds of medicines. Sometimes model and output are given. I want to be able to calculate the input or the parameters that led to the output. So there are three objects: input, model, output. Input, model, getting the output is called forward problem. Input, output given, understanding the parameters of the model is an inverse problem. I have a model, I have output, I don't know the input. What kind of input would have given rise to these kinds of output situations? With me? So these are the, so data to model is called data mining. Data mining is an inverse problem. So what is an example of where all these problems are clubbed together? Time series analysis. In time series analysis, what is that that's given to you? I'm given the IBM stock price for the past 30 years. Please model the the movement of IBM stock price and make a prediction how the price varies tomorrow, next month, and so on. So there you are simply given a bunch of data. In the case of time series analysis, there is no causality. In physics, there is causality. In science, we depend on causality. There's a cause and effect. So in time series analysis, we fall back only on correlation. So I want to now emphasize, to make prediction, I should have either causality or correlation. In science, all the models are causality-based models. Newton's law, if there is a force, there must be an acceleration. For every force, there is an equal and opposite reaction. Okay? All the problems we learn to solve in physics, in chemistry, they are all causal models. So if I have a causal model, I can run the model forward in time, make a prediction. In a time series, there is no causality. Of course, there is causality. There are lots and lots of factors. If there is a war in some part of the world, the gasoline price goes up. But what is the effect of a war? Can I quantitatively predict the impact of a war or some other strike in a company or a blowout in a plant? We all know the supply is going to be disrupted, the price goes up. We know this general relation, but we don't know how to quantify them. So in those cases, what do we do? Instead of searching for a causal model, which is very difficult, we settle for models based on correlation. So time series models are all based correlation. So either use causality or correlation, you get the model. Once you get the model may have lots of parameters unknown. In the case of time series, the data gives rise to the model. I use the same data to be able to estimate the parameters of the model. And once I estimate the parameters of the model, I'm going to make predictions. So now you see the role of data mining, data assimilation, prediction, how they are interlaced together. So what are the three pillars of data science? Data mining, DM, is an inverse problem. That process going from data to model. So whenever you are doing data mining, remember Kepler. To me, Kepler is the model data miner. Not that Copernicus, Galileo are not, but Kepler did much more fundamental based work. With me? Data assimilation is an inverse problem. The process of combining the models with data to be able to estimate the parameters. So when you are doing parameter estimation, remember Gauss. Gauss is the first one to be able to show the pathway to estimate. Prediction is a forward problem. So to me, data mining, data assimilation, and prediction, DM, DA, and P, are the three pillars of data science. No matter what branch of science you are interested in, these are the basic things you do. So this should give you a broad-based idea about what data science is all about, what data scientists do, and so on. Now I would like to come back to the Indian scene. I've been only talking about the Western contribution to data science, but India has contributed even far earlier. We don't get as much credit for it, so I'm going to give you a glimpse of the Indian astronomy, in the early days of Indian astronomy. Please understand, to me, data science began in astronomy. So in India, we have divided the time into yugas. Krita Yuga, Treta Yuga, Dwapara Yuga, and Kali Yuga. We are supposed to be in Kali Yuga. Once Kali Yuga ends, it says it will repeat. Ramayana happened in Treta Yuga, about 7,000 years ago, according to current estimates. Mahabharata happened in Dwapara Yuga, about 5,000 years ago. Why am I talking about this? There are important consequences relating to data science as early as those days. In Valmiki Ramayana, he talks about the time of birth of Lord Rama. what we now call horoscope. So according to Valmiki Ramayana, at the time of birth of Rama, Sun, Moon, Jupiter, Saturn, Mars, Venus, Rahu, Ketu. So the 360 degrees is divided into 12 sectors. They would like to be able to specify the positions of various planets in these 12 sectors, and he was able to precisely predict. Think about it for a moment now. So during Valmiki's time, he knew the positions of various planets. Are you with me? But we don't find this in any book, English-based book. Valmiki was not an astrologer or an astronomer. He was a poet. So he must have been using the concurrent knowledge available at the time to specify the date of birth of Lord Rama. Whether you believe Ramayana or not, that's not the point. The point is he was able to specify the positions of the various planets with respect to the sun. It is now said that nobody has inherited a horoscope as Lord Rama did. But that's a different problem. But I want you to know that we knew the positions of various objects at that time. Are you with me? But we talk about Copernicus, Galileo, Kepler. I'm not trying to take away the importance of that, but we had much deeper knowledge about astronomy much earlier than we may want to realize. The great, okay, that you can say, very previous yugas. Let's come back to Kali Yuga, our own time. Aryabhatta in Gupta dynasty, he knew, he had computed the earth was spherical. He had computed the diameter of the earth. He has also estimated the duration of the year to be very close to 365 days. And he also knew that the earth was moving around the sun. But the credit goes to Copernicus. All of you with me? So there are lots of astronomers like that, Varahamira, Brahmagupta, Bhaskara, and a whole host of scholars. Are you all with me now? So does it make you wonder what kind of science they had? What kind of devices they used to collect observation? What kind of models they used? So data mining, model building, data assimilation was at its peak in our own country. What is the difference? India was never India. India was a union of 250 plus kingdoms. The kings were fighting each other. Of course, they supported the poets. They supported wise men. But these wise men and poets, they wrote everything in Sanskrit. And Aryabhatta and other people, they did not write in the lingo of the modern mathematics. They wrote as slokas in Sanskrit. They lay hidden. These kinds of results lay hidden in the literature waiting to be uncovered. Of course, now everybody says, well, India had a very sophisticated past. They had great thinkers. But nobody is willing to change the textbooks. Are you with me? Physics book still talks about only Kepler. Aryabhatta's result has not found its way into. So what I'm saying is that in those days, the kings supported the wise men, but they never worried about publicizing their results to the outside of their own kingdoms. With me? That's an important aspect I want you to be able to realize. Now I'm going to get a little bit more deeper into introducing you to some mathematical things that paves the way for other topics. So data is the key, model is the key. Who are the key players? Data and model. Now I'm going to talk about models in data science. I come from an applied mathematics discipline. I'm interested in models of any and every kind. So I'm now going to talk to you about different types and varieties of model that one has to deal with in the overall parlance of data science. You in your particular work may be involved in only one class of models, but I'm going to give the properties of the whole galaxy of models that data scientists have used in the past. So models are based on causality or correlation. I already talked about that. Cause and effect. I'm not feeling well today because I ate a little bit more of hot food last night. That's causality. Correlation. Correlation is a very weak relation. So weather prediction, I'm sure you have seen that, right? The past 4 days. It is predicted that this week, during Thursday, Friday, Saturday, there may be rain, light rain up to 5 centimeters with a probability 80%. With me? So that's a statement which is probabilistic. It may not happen. If it happens by chance, the chances are no more than 80%. And if it did happen, it's going to be like variety. So causality versus correlation. Model can be implicit or explicit. The differential equation that describes the motion of the Earth around the Sun, that's an explicit model. The neural network that helps to classify the letters of the alphabet, that's an implicit model. We know it works, but we don't know how it works, why it works. A model can be dynamic or static. The ellipse is a static object, but a differential equation represents the motion of an object. That's a dynamical model. So it could be, the dynamical model can be either an ordinary differential equation or a partial differential equation depending on the phenomenon. In chemical engineering, many of the models are PDE. In electrical engineering, electric circuit analysis, we use a lot of ODEs. I'm an electrical engineer by training. Model can be deterministic or stochastic. The model that describes the motion of the Earth around the Sun, that's a deterministic model. Please understand, we are able to predict the occurrence of the lunar and solar eclipse for the next 100 years with absolute precision. That's determinism. With me? Time series models. What's the likelihood price of IBM stock tomorrow? IBM stock may rise by 10% with a probability 70%. Are you with me? A deterministic model versus stochastic model. Stochastic model means the outputs are random. A model can be linear or nonlinear. Yeah, I don't have to tell you. Ax is equal to b is a linear equation. Ax squared plus bxy plus cy squared, that's a nonlinear equation. A model can be a nonlinear model or a linear model. A model can be in discrete time or in continuous time. The stock market opens at 9 o'clock at every working day. It is closed during the weekend. The stock price that you get is always the ending stock price at a given day. During the day, the price varies. But when they say today, yesterday's price is the ending price. So there the time is measured in terms of days. Hourly rainfall. With me? Annual birth rate. They are discrete time. Continuous time. The motion, the position of the Earth as a function of time. It changes continuously. Space can be discrete or continuous. Almost all the models, they deal with only continuous space. What is a discrete space model? I don't know how many of you have heard of this. There is a class of models in random processes called Markov chain. There is only a set of finite states, the discrete state, and things keep jumping from one to the other. For example, let us take a car. A car either works or doesn't work. If it doesn't work, it may not be working for a million reasons. So what is the model, discrete state model for a car? Given that it is working today, what is the probability it will work tomorrow? Given that it is working today, what is the probability it may not work tomorrow? If it doesn't work, I cannot make it work until I do the repair. So the state of a model, the state of a car can be described by two states. All of you? That's the idea. So look at this now. You can have a causality based, explicit, dynamic, deterministic, linear model in continuous time and continuous space. Are you with me now? And what is that? The motion of the earth around the sun. I can have a correlation based explicit model, which is a dynamic model, which is a stochastic model, which is linear, continuous time and continuous space. What is, I'm sorry, discrete time and continuous space. What is that? Time series models. The number of deaths in the highway. Are you with me? Come on, guys. Why are we talking about the number of deaths in the highway? Because I want to understand the reasons for the death. Is it because the structure of the road, or is it because of speed, or is it because of the driver's fault? If you want to be able to reduce the driver impact, you have to strictly impose seat belt laws. Seat belt does save time. I'm sorry, lives. With me? In some countries, you have to, the people in the front seat and those who are in the back seat also must wear belts. Otherwise, the police can ticket you. Safety does. So safety measures can reduce the accidents, the impact of accidents. With me? So these are all the different types of models. Now, observations are data. To me, observation is data, data is observation. So I talked about different types of models. Now I want to talk about different types of data. Why? That's what a data scientist should be. A data scientist should be able to work with any form of data, with any form of model. And that's where I come from. Applied mathematics. So time series data, what is an example? Daily maximum temperature in the city of Madras. Spatial data, what is the current COVID infections across the state of Tamil Nadu? Spatiotemporal, monthly rainfall in the state capital Madras. I used to call it Madras because they changed the name Chennai after I left town. But I still call it Madras, but you all know what I'm talking about. So spatiotemporal. So time series data, spatial data, spatiotemporal data. In economics, they are also interested in other type of data. For example, that's called tabular form of data. In each state there are agricultural products being produced because we have to feed 1.4 billion people, right? So we are interested in the agricultural production. So state, agricultural product, how much tonnage each state produces, each type of agricultural product in each state. So that's a three-dimensional object. Are you with me? States, agricultural product, and then the entries in that. How many tons of wheat in Tamil Nadu? How many tons of wheat in Telangana? So on and so forth. The last form of data is called data matrix. In here, I have a matrix X. It has n columns, x1 to xn. Each column vector is a d-dimensional vector. I'm sure you all understand basic aspects of matrices. A d-dimensional vector is a point in a d-dimensional space. A two-dimensional vector is a point in a 2D plane. A three-dimensional vector is a point in a 3D plane. A d-dimensional vector is a point in the d-dimensional space. So this matrix having n columns, each column is of length d, refers to the distribution of n points in a d-dimensional space. So I have a finite number of points in a large dimensional space. I want to be able to understand the distribution of this set of points and the geometry as to how they are going to be aligned. N represents, so the n points in a d-dimensional space, n could be large, d could be large. In big data analytics, both n and d are large. One of the interesting things is big data analytics. So what makes the big in big data? So there is n, there is d. If d is large, the larger dimension. If n is large, larger number of samples. So we often consider larger number of samples in a large dimensional space, and that's the ultimate challenge in data science. So those are examples I have already given there. So, in summary, data could be in time series form, data could be in spatial form, data could be spatio-temporal form, the data could be in the tabular form. The tabular form is a kind of a spatio-temporal. Please understand, the agricultural product state-wise and year-wise is, are we producing more rice this year than last year? If it is less, we want to understand why, how, and so on and so forth. And then the last form is data matrix form. Some of you in your own arena may deal with only one form of data, maybe time series, maybe spatial data. A geologist interested more in spatial data. In weather science, they are interested in spatio-temporal data. With me? Matrix form of data, we can reformulate the problem in other areas as to one of matrix form of data. So, we will talk about some of these things as we go by. Now, I am talking about some of the known methods in data science. So, as I told you, data science is not new. If it is not new, it must have been in the development. If it has been in the development, people must have used various techniques to develop the methods of data science. As I told you, it was not born in day before yesterday or 10 years ago. It has been there over the millennia. So, what are the tools and techniques people used to solve problems related to data science in their own discipline? And that's what I'm talking about here. Statistical estimation theory, which I now call as data assimilation. Kalman filtering technique is a method for both assimilating and forecasting. Those of you who may be doing electrical engineering, you should know about Kalman filtering. If not, it's simply a statistical method for making predictions within the context of stochastic dynamical systems. I have a random dynamics. Multivariate regression analysis in statistics. Data reduction technique, PCA, that's in statistics. Classification or clustering. Last year I came here, I gave 5-6 lectures on clustering. I think they have a copy of the videos on clustering. What's the concept of clustering? So let's talk about that. Humans. At the top level, we are all alike. We all have a nose, ears, legs, this and that. But if you look at a finer thing, men, women. Then we say, hey, he looks like a Japanese, he looks like a Chinese, he looks like an Indian, he looks like an African, he looks like a white, he looks like an American, he looks like a red Indian. Don't we say that? So we have a natural ability to be able to distinguish people by their looks. We say, hey, look like that guy looks like a foreigner. This guy looks like a fellow from North India. Don't we say that? That's right. Even without talking to anybody, just by looking at a face of a person for under 30 seconds, you can classify a person. So humans have the internal ability to classify people based on the features they observe. I can't describe, but I can tell that this person is Japanese, that person is a Chinese, this person is Indian. We all do that, right? So what is it we want? What is artificial intelligence? If you can make a machine do what humans do, inducing the human intelligence into algorithms and machines is artificial intelligence. So you can readily see data science includes artificial intelligence as a part of it. To me, data science is an all-embracing umbrella that includes artificial intelligence as well as a part of it. ANN is artificial neural network, pattern recognition. SVM stands for support vector machine. DNN stands for deep neural networks. There are association rules, decision trees, probabilistic networks, machine learning, genetic algorithms, random field spatial data analysis. These are the tools and techniques that scientists have used over the years to collectively promote, grow the various parts of data science. Am I providing a global view of what data science is all about? And it is this realization that data science has been around for a long time and there are already built-in techniques. And I'm working in this ocean, but I want to add few more to that. So you need to understand what has been done over the years. So summary, data mining seeks to uncover the structure or patterns in the data so that we can summarize the intrinsic properties of the data generating process. The data generating process, once I understand, we get a model. We call a rule, law, or a model. The goal of data assimilation is to fit the model to data. The fitted model has a better predictive power. The goal of data assimilation is to fit the model. The fitted model has a better predictive power. So data mining, data assimilation, and prediction are parts of a continuum, and they form the three pillars. There's another term here I want to introduce here, predictive science. I'm sure you all have heard of it. Predictive science, the ultimate goal is to do a prediction. So is data science different from predictive science? No, I would like to call the generically as data science. Predictive science is a part of data science, or one of the aims of data science is to be able to understand this notion of predictability with me. So that is the animal that we now come to call as data science, the three pillars, DM, DA, and prediction.